Hey there, it's Shannon Matchick-Myers, and today we'll be covering section 4.4 from our workbook, which covers eigenvalues and eigenvectors and diagonalizing matrices. So let's check it out. The eigenvalue problem. One of the most important problems in linear algebra is the eigenvalue problem. When A is an n by n, matrix, do non-zero vectors x and Rn exist such that Ax is a scalar multiple of the vector x? The scalar, denoted by lambda, is called an eigenvalue of the matrix A, and the non-zero vector x is called an eigenvector of A corresponding to lambda. Definitions of eigenvalue and eigenvector. Let A be an n by n matrix. The scalar lambda is called an eigenvalue of A when there is a non-zero vector x such that A times x is equal to lambda times x. The vector x is called an eigenvector of A corresponding to lambda. Note that an eigenvector cannot be the zero vector. Why not? If you have the matrix A times the zero vector, and you set that equal to lambda times the zero vector, what are we going to get? Beautiful. We'll just get the zero vector is equal to the zero vector, which is just trivial, right? So here we go. Example 1, let's determine whether x is an eigenvector of A. All right, so let's check it out. We've got A times x equal to some lambda times x. A is the matrix, -3, 10, 5, and 2 going across. And then x is -8 and 4 going down. And we want to find a lambda where you've got lambda times x is equal to the product on the left. All right, well, when we multiply these two matrices, we're going to get 24 plus 40, which is 64. And let's see, -40 plus 8, we'll have -32. And then that would equal to -8 lambda and then 4 lambda. And both have to be true in order for this to work. So if we take a look at this, we would have -8 lambda would have to equal to 64. And what else? -32 would have to equal to 4 lambda. So on the first equation, we would get lambda is -8. And on the second equation, we would get what? Sorry, I switched them around, but we would have lambda is equal to -8 as well. So they're the same. We would say yes. And what would lambda be? Lambda would equal to -8. All right, what about this next one, part B? A will still be the same. So let's check it out. Setting up the product on the left, we'll have the matrix A that I'm writing. And then we want to find out if there's a lambda that will work. So doing the multiplication on the left, we'll have -15 plus -30 would give us -45. And then 25 plus -6 will give us +19. And then on the right side, we'll have 5 lambda and then -3 lambda. So 5 lambda equal to negative 45 will give us, good, a lambda would be equal to negative 9. But here, negative 3 lambda equal to 19 would give us lambda equals negative 19 thirds. And so we would have to say no for this one because the lambda doesn't match. All right? Okay, so now let's move on to our first theorem here for eigenvectors. If A is an n by n matrix with an eigenvalue lambda, then the set of all eigenvectors of lambda together with the zero vector, so I'm just going to write this in math, so x such that x is an eigenvector of A and union the zero vector is a subspace of Rn. And this subspace happens to be called the eigenspace of lambda. So the set X such that X is an eigenvector of A union the zero vector is a non-empty subset of Rn, since this set contains the zero vector. Good so far? So now if we let U and V be eigenvectors. So if this is true, then A times U is going to equal to some lambda times U, and A times V will equal to some lambda times V. And why don't we also let C belong to the real numbers? So now we're all set to show closure under addition and scalar multiplication. So let's check it out. A times U plus V is going to equal to what? Beautiful. A times U plus A times V. But what will that equal to? Good. Lambda times U plus lambda times V, which is good. Lambda times U plus V. These are all properties we've shown before. So we've got closure under addition, and what do we do next? A times C times U is equal to, good, C times A times U, which will be C times lambda times U, which is lambda times C times U. So we've shown closure under scalar multiplication. And now we've shown what is to be shown, right? Okay, so next up, eigenvalues and eigenvectors of a matrix. Let A be an n by n matrix. An eigenvalue of A is a scalar lambda such that the determinant of lambda times I minus A is equal to the scalar 0. Now, just so you know, eigenvalues are shown in different ways. Oftentimes it's shown as the determinant of A minus I times lambda, which ends up being the same, okay? Just so you can see, this would end up being equal to the determinant of -1 times, good, lambda I minus A, which is what? Absolute -1 times the determinant of lambda I minus A, right? Which of course is just the determinant of lambda I minus A. All right, so either way that you remember them is fine. So the eigenvectors of A corresponding to lambda are the non-zero solutions of lambda I minus A times x is equal to the 0 vector. So to get the eigenvalues, you set the determinant of this lambda I minus A matrix equal to the scalar 0. To find the eigenvectors, you multiply the matrix lambda I minus A times x, and you set that equal to the 0 vector. Good, good? All right, so the equation, determinant of lambda I minus A equal to 0, is called the characteristic equation of A. When expanded to polynomial form, the polynomial is called the characteristic polynomial of A. This definition tells you that the eigenvalues of an n by n matrix A correspond to the roots of the characteristic polynomial of A. All right, so let's take a look at an example. We want to find A, the characteristic equation, and B, the eigenvalues and corresponding eigenvectors of this matrix A, which is shown below. So here we go. Lambda times the identity matrix for a 3 by 3 matrix minus A will be what? Beautiful. You're going to have lambda times 1 minus 3 is lambda minus 3. And then all these other signs will flip here in that row. And then we'll have a 0. And then lambda times 1 minus 0 is just lambda. And then the sign will flip here. And we'll have 0, -2, and then again lambda. Good so far? Okay, so here we go. We need to find the determinant, don't we? So why don't we go ahead and expand off of that first column? I think that's going to be easiest. And when we find those eigenvalues, which will be part A, we want to find the eigenvalues. It might just be 1 with a multiplicity, so we'll just say, put the S in parentheses. And to do this, what do? We're going to set the determinant of lambda I minus A equal to 0 and solve. Cool, cool? All right, so here we go. Lambda times I minus A, and that equal to 0 will be. Well, we just found lambda times I minus A. So to find the determinant of that, what do? We're expanding about that first column. So we'll have lambda minus 3 and then times the determinant corresponding to the times the determinant lambda, negative 2 lambda going across, and that's all going to be equal to 0. So this will be lambda minus 3 times lambda squared minus 4. That's all equal to 0. All right, well, we've got two factors equal to 0, so let's use that 0 product property, and we'll get lambda minus 3 is 0, or lambda squared minus 4 is 0. Good so far? Awesome. And then coming up here, what are we going to have? We'll call this lambda 1 will equal to 3. And then we have lambda squared is positive 4. So lambda would be plus or minus 2. So we'll say lambda 2 is negative 2, and lambda 3 we can say is 2. Good so far? Awesome. All right, so now what's our next job? I think I went a little bit beyond, right? The characteristic equation is what? Beautiful. So right here was our characteristic equation. And so we're done with part A. All right? So going on, we're starting now with part B at this juncture. Right? So this part of part B are the eigenvalues. The eigenvalues of A were lambda 1 is 3, and then lambda 2 is negative 2, and lambda 3 is 2, right? So now the next part, the next job, is to find the eigenvectors. Good so far? So to find the eigenvectors, of A corresponding to, we'll say lambda I, what do we need to do? Beautiful. We need to solve lambda I times the identity matrix minus A times the vector x is equal to the 0 vector. So, moving right along, let's start with lambda 1, and that was equal to 3. Good so far? So, here we go. Lambda 1 times I minus A times the vector x equal to the 0 vector is what? Well, lambda 1 was 3, so we'll just have 3 times I minus A times x is equal to the 0 vector. And remember, we have lambda I minus A, so we just plug in 3 wherever there's a lambda. So that's going to give us, in the diagonal, let's see, 0, 3, and 3. So we'll have and then we've got a 3 by 3 matrix, so this has to be a 3 by 1, the x vector. And this will be equal to the 0 vector. Cool so far? Well, we've solved stuff like this a lot, haven't we? We basically look at the augmented matrix and what? Row reduce. So we're looking at 0, negative 2, negative 1, 0, 0, 3, negative 2, 0, 0, negative 2, 3, 0. So notice we're really just solving what? A homogeneous system of equations, right? So to save some time, I've prepared the reduced row echelon form. So the reduced row echelon form will be 0, 1, 0, 0, 0, 0, 1, 0, and then a row of zeros. And then what will we have? So what does that mean? That means that, beautiful, x2 is equal to 0, x3 is equal to 0, and what about x1? It didn't show up there, right? So isn't x1 just going to be a free variable? So why don't we say x1 is equal to r? Good so far? All right. So here we go. I've found the first eigenvector. Isn't that exciting? So if we look at our x vector, we've done this before. That's going to be equal to 0, 0, r. And if we factor out r, that would give us what? 0, 0, 1. Cool so far? So what we found out right here was the following. The eigenspace of A corresponding to lambda 1 equal to 3 is the set r 0, 0 such that r belongs to the real numbers. Good so far? All right. So we're good there. Now, what about the next one? So for lambda 2 equal to negative 2, let's see what we get. Well, we'll have negative 2 times I minus A times x equal to the 0 vector. And what will we get for that? Negative 2i minus A. Beautiful. The diagonal will be what? Negative 5 and then negative 2, negative 2. So we will have negative 5, negative 2, negative 1, 0, negative 2, negative 2, and 0, negative 2, negative 2 times our x vector, which is x1, x2, and x3 equals the 0 vector. So row reducing, we'll have what? All right, so for this one, the reduced row echelon form of the matrix will be 1, 0, negative 1/5, 0, 0, 1, 1, 0, and then a row of zeros. So that gives us that x1 minus 1/5 x3 is 0, and x2 plus x3 is 0. So this time x3 will be our free variable. So if x3 is equal to s, we'll call it, then this one here, x1 would be 1/5 times s, and then x2 would equal to negative s. Okay, so far? And so the eigenspace of A corresponding to lambda 2 equal to negative 2 is the set 1/5 times s, negative s, and s, such that s belongs to the real numbers. Good so far? Okay, so I need to add a page. Sorry about that. So for the third one, what will happen is we'll have for lambda 3 equal to positive 2, 2 times I minus a, that matrix, times x equal to the 0 vector will give us negative 1, and then negative 2, negative 1, 0, 2, negative 2, 0, negative 2, 2, and then x1, x2, and x3 for our x vector equals the 0 vector. All right, so what are we doing? We need to find the reduced row echelon form for the homogeneous system. And this will be, once you simplify on your calculator, this is going to end up being 1, 0, 3, 0, and then 0, 1, negative 1, 0, and then a row of zeros. And then that gives us that x1 plus x3 is 0, x2 minus x3 is 0, and then if we were to let x3 equal to t, we'll have x1 will equal to negative t, x2 will equal to positive t. So the eigenvector of A corresponding to lambda 3 equal to positive 2 is the vector negative t, t, and t, such that t belongs to the real numbers. And you didn't have to use different variables for the free variables. I just did it to make it look easier for you. Okay, so that is the finish of the problem. So we've got, this is one of our eigenvectors. Here's another one. And there was that first one. Cool, cool? All right, so let's see what we've got next on the agenda. I wanted to bring your attention here, just so you don't confuse the wording. As we learn, the eigenspace of A corresponding to some lambda is all the possible eigenvectors of lambda, which are non-zero, union the 0 vector. So technically this one is correct for eigenspace. All right, these eigenspaces are correct. But when I said eigenvector right here, I should have said eigenspace, or I should have excluded t being able to be 0, because eigenvectors are non-zero. Cool, cool? So let's just go ahead and find a basis for each of those eigenspaces. So to find corresponding eigenvectors to each of the lambdas, you just need to let the free variable be equal to something which is non-zero. If you had more than one free variable, as long as they're not both zero at the same time, you're good. So let's go ahead and find eigenvectors corresponding to the lambda i's are. So for lambda 1 equal to 3, let r equal to 1. So then that eigenvector that corresponds, if we let r equal to 1, would be what? Beautiful, 1, 0, 0. And then for lambda 2 equal to negative 2, again, if we let that parameter equal to 1, what would we get? Good. We'd have 1/5, negative 1, and 1. And then for lambda 3 equal to positive 2, if we let t equal to 1, we would have, beautiful, negative 1, 1, and 1. And what you'll find out in the next section is this. We let these each equal to a P1, P2, and P3 column vector, and that's going to help us diagonalize a matrix. Groovy? Okay. So I'll box this part. It turns out that eigenvalues of triangular matrices are on the main diagonal. So if A is an n by n triangular matrix, then its eigenvalues are the entries on its main diagonal. So that's always a very useful theorem to remember. So if you have this here is what, a lower triangular matrix. So the entries on the main diagonal are negative 5, 7, and 3. So we'd have lambda 1 is negative 5, lambda 2 is 7, and lambda 3 is 3. Eigenvalues and eigenvectors of linear transformations. A number lambda is called an eigenvalue of a linear transformation where t is going from some space v to v when there is a non-zero vector x such that t at x equals x. The vector x is called an eigenvector of t corresponding to lambda, and the set of all eigenvectors of lambda with the zero vector is called the eigenspace of lambda. Okay, let's tackle example 4. Basically with this one, we have been given this matrix A, which is relative to the standard base. But you know what? Unfortunately, I'm very sorry. There is a typo here. This should have been A equals 6, negative 3 going across, and then negative 2 and 1 going across on that second row. So we want to find the eigenvalues of A, a basis for each of the corresponding eigenspaces, and then the matrix A prime for T relative to the basis B, where B prime is made up of these basis vectors that we'll find in part B. All right, so for part A, finding the eigenvalues. Well, what do? Beautiful. We need to find lambda I minus A. So that's going to end up being what? Lambda minus 6. And then it'll switch this to positive 3. And then positive 2. And then we'll have lambda minus 1. And so then finding the determinant of that, so remember we're solving this equation, lambda minus 6, 3, 2, lambda minus 1. The determinant of all that equal to 0. So what are we going to get? Lambda minus 6 times lambda minus 1 minus 6 is equal to 0. So let's see, what do we get here? Lambda squared minus 7 lambda plus 6 minus 6 is 0. And so this simplifies to be lambda squared minus 7 lambda is equal to 0. And then factoring, we will have lambda times lambda minus 7 is 0. So lambda 1 is 0 and lambda 2 is 7. Good so far? Very good. So that is going to be the result for part A. Part B, we need to work on basis for eigenvectors. All right, so when we do that, let's go ahead and box this one because we're all done. And then here, for lambda 1 equal to 0, let's see what happens. Well, when I plug in 0 for lambda in this matrix here, I will get negative 6 and negative 1 along that main diagonal. So I have negative 6, 3, 2, and negative 1. And then times that x vector, and that has to equal, remember, to the 0 vector. We're working with lambda I times I minus A times xi equal to the 0 vector. I'm just making it a general equation for the eigenvectors. All right, so we just need to row reduce. So if we start with this one, you don't need to have the zeros, but it just helps us keep track. What do we need to do with this guy? Well, if I have a row 1 plus 3 row 2 for a new row 2, what will I get? The first row stays the same. The second row will be 0 and then 0, 0. Cool, cool? All right, so what did that land us? That tells us that negative 6x1 plus 3x2 is 0. And so x1 is going to be positive 1/2 times x2. So our first eigenspace, call it space x1, would end up being 1/2 t, comma t, such that t belongs to the real numbers. So this here is the eigenspace corresponding to lambda equal to 0. And the basis will be, we're going to call it P1, say, and that would be, just let t equal to what, 1, and we'll get 1/2, comma 1. Good so far? Awesome. And then for, I guess we'll need another page on this one. So that's one of our bases. Actually, you know, we'll just leave it as P1. All right, and then for lambda 2 equal to positive 7. So again, we're using this matrix to plug in lambda equal to 7. So when we do that, we'll have 1, 3, 2, and 6. All right? And that's going to be times x1, x2 equals to the 0 vector. And so we'll have 1, 3, 0, 2, 6, 0. If we reduce, do you see if we do -2, row 1, plus row 2 for a new row 2, we will get the same first row. Our second row will be 0, 0, and 0. Good so far? Awesome. So this will be what? x1 plus 3x2 is 0. So then x1 is equal to -3x2. And then our second vector space, eigenspace, x2 would be good, -3t, comma, t, such that t belongs to the real numbers. And then a basis, call it P2, will be, if we let t equal to 1, we get -3, 1. Good so far? Very good. So this is our second one. So now we want, our part C is telling us to use this basis, B prime, okay, is what we just found. And so our first vector was 1/2, 1. And our second vector was -3, 1. We know that B was equal to the standard basis that was given. And so that's 1, 0, 0, 1. So let's see what we get. Well, if I adjoin B prime to B, right, that's going to give me 1, 0 going down, 0, 1, and then 1/2, 1, -3, 1. So what does this give me? Doesn't it give me I2 and, good, P? Very good, very good. All right, so P inverse, therefore, I'll do a different color for that. P inverse will be, remember, 1 over the determinant of P times, so we'll have 1 over 1/2 plus 3 would be what, 7/2, I believe. And then we need to switch around the main diagonal and then swap the signs on the other one. So that's P inverse. And then when I put this in, we'll have 2/7, 6/7 going across, -1/7, and 4/7. Cool, cool? All right, so now remember that A prime is equal to P inverse times A times P. So A prime will be, this was our P inverse, A was the one given in the problem that we were working with, so 6, -3, -2, 1. And P, we have the 1/2 -3 going across, 1 and 1. So let's see what we get. A prime equals 12/7 minus 12/7 is 0. And then we'll have -6/7 plus 6/7 is 0. And then -6/7 minus 8/7 is negative 14/7, which will be -2. And 3/7 plus 4/7 is 7/7, which is 1. So that's the product of these first two. And so we'll have A prime will be this matrix that we just found times 1/2, -3, 1, and 1. So A prime will be equal to 0, 0. And then -1 plus 1 is 0. And then 6 plus 1 is 7. And so look at that. Isn't that kind of groovy? Isn't it diagonal? Yes, one of the values here is on the main diagonal is 0, but you still have a diagonal matrix. Isn't that very groovy? Okay, so we're all done. A couple things to observe here. The entries on the main diagonals, aren't they equal to, where do we find those eigenvalues? So remember we had these, lambda 1 is 0, lambda 2 is 7. And look, see how they're on our main diagonal? So that's something to observe. And the other thing to observe is we were able to find a matrix similar to A, which was diagonal, which is pretty powerful stuff. All right, so I hope you have a wonderful morning, afternoon, or evening whenever you're watching this show. And if you like what I'm doing, hey, please subscribe and tell all your friends. Bye.